Hello and welcome back to part 11 in the Introduction to Calculus series. Today we'll cover a more advanced method for computing derivatives. You won't use this technique very often, but it's basically, sometimes it's the only way to do the derivative of a function. So if we look what kind of functions we've already covered like trigonometric functions, just regular polynomials. We've covered logarithms, we've covered exponentials. Right, but what if we say combine some of these functions? Now, well, oftentimes you can just use the chain rule, like in cases like this. But what do you do when you have a function, let's say, that is x to the power of x? Because that's a totally valid function, but what kind of rule would you use? You can't use the regular power rule for polynomials, because this in the exponent, that's not a number. And pretty much the same applies to the exponential rule, that you just multiply by the ln of the base, because again, that only works if the base is just a number. So what do? Well, we're going to use a little bit of a trick now. So I'll just rewrite this quickly as y equals x to the x. Alright, so what we're going to do is we're going to actually not differentiate y directly, but we'll first of all manipulate this equation a little bit. So what we're going to do is we're going to take the natural log on both sides. So the natural log like that, and by that, by the power identity, I guess you could call it, this x jumps forward and becomes a factor, like so. And on the left side we still have ln of x, or ln of y rather. Alright, so now what we're going to do is we'll just take the derivative on both sides. Alright, so let's try that. So we'll take the derivative on both sides. That won't actually change, the equality, I suppose, the truthfulness of this statement, because if you have two functions that equal each other, like f of g, f of x equals f of g of x, and you take the derivatives, they're still the same, because you kind of say that this is f and you'll still get the same thing, right? So we can take the derivative on both sides, so let's do that. But now we've run into a bit of a problem, because the derivative on this side goes fine, right? That becomes, by the power rule, that will become first just normal divided by x, because the derivative of ln of x, that's just 1 divided by x. Add on to that just the derivative of that times the original of the second. This just becomes ln x like that plus 1, right? That's easy enough. But now how do we do this? Because we don't really have an x here. And if we were to just substitute in y equals x dx, then we just have our same problem. But now what we can do, we can actually make use of the chain rule in a very specific way. So what we can say is that y is just some function of x. We don't really know what, but we'll just write this down. So it is some function of x. And if you have, so now we have the natural log of just some function of x. We don't really care about the specifics yet. And let's just differentiate that. So what we'll get is, we'll just get 1 divided by y, and then we have to multiply by the chain rule by the derivative of the inside. So that just becomes the derivative of y. We don't really know what that is, but it's just the derivative of y. And now we can say, what do we want to know? Well, we want to know the derivative of y, right? So what we can do is we can actually just multiply. So let me rewrite this like so. Alright, that's the thing we have right now. So what we can do is we can multiply both sides by just y, and then we'll be left with the derivative of y is y times ln x plus 1. And now we can substitute y equals x to the x, and that will give us the derivative of y equals x to the x times ln x plus 1. And that is our final answer. So what we did here, just to sum up real quick, is first of all we manipulated our original equation, if you can call it that, to contain only functions that we can differentiate, because this part goes fine, right? And then then we differentiated the ln y by treating y as a function of x and applying the chain rule like that, and then we solved for the derivative of y, and that just gave us, well, the derivative of y, right? So let's do one more example, because it's kind of, I think this one is this one's the cleverest derivative rule I've seen yet. Alright, so let's do a bit of a complex example. So something like this. So it's a bit messy, but it'll illustrate the point. So we have y equals x to the power of e to the power of sine of x. So that's a little bit more complicated. So again, we can't just use any of those two rules, because we have x, and then eventually we'll have some other x here, and that messes things up, if you will. So we'll just use the same trick here. We'll do the natural log on both sides. It's important to note the natural log doesn't always work. Sometimes you need to do something else, but in this case, you don't. Well, you know, this is the way to do it. ln x. And now again, we have two functions that we can differentiate. So this one again will be just 1 divided by y. That's just the derivative. And then we have to multiply by the derivative of y. This one's a little bit more complicated. Again, we'll use the product rule. So we'll just copy this. And divide out by. Yeah, right, because you have to do the derivative of ln x. Yes, that is just 1 divided by x. Add on to the derivative of e to the power of sine of x. Well, we'll use the chain rule for this. So we have, well, e to the something remains the same, so we can just copy that. And then we have to multiply by the derivative of the inside. That's going to be the derivative of sine of x, so that'll be cosine of x. And then we just multiply by that. Alright, now we solve for the derivative of y. It's going to be like that, so we have to multiply by y. I'm actually going to factor out e to the sine of x, like that. Alright, 1 divided by x plus cosine x ln x. And then we can substitute in our original equation of y, which will give us final equation x to the power of e to the power of sine of x times e to the power of sine of x, kind of weird, all multiplied by 1 divided by x plus the cosine of, like that, multiplied by, obviously. Alright, so that wraps up implicit differentiation. As you can see, it's a bit more of a complex rule, like it's more niche rule also, because you don't often see functions like this or functions like x to the x, but it is a nice technique anyway, to differentiate functions that wouldn't have an easy derivative otherwise with just regular rules. So, well, that wraps it up. Thank you for watching, and I'll see you in the next part. Bye bye.